And we've got, starting from the current slide, and I think I've made all the announcements to you before. I'm pretty sure they got, when they published the final exam schedule, it came out wrong. They have Monday as the first day of finals, and the academic calendar and the administrative calendar have Tuesday, the 30th, as the first day of finals, going through the following Monday. Are you graduating this term? No. Okay. So if any of you are graduating this term, you'll need to let me know, because you have to have your work in sooner than people who aren't graduating. So anyway, we'll continue with that later. Now let's see. My memory is that we were on example 3 on page 838. This is chapter 12, vector value functions in 12.3, velocity and acceleration. Now, I've noticed the last couple of, or a few times recently, I don't want to say it's the last 2 or 3 times, but the few times recently when I've been typing in at the end of the class, either I didn't hit the 1 hard enough, but I've noticed that the names of the files have been 2.3 or 2.1 or 2 point something, not 12 point. So that's still us. That's still the right thing. It's just that either I didn't type the 1 or I didn't hit it hard enough and didn't catch it until it was already out there, and then it's kind of a pain in the neck to try to make the changes once they're on Blackboard. I mean, not Blackboard, YouTube. So it's out there under the wrong names anyway. But they're all in the playlist correctly. Even if it says 2.3, that's not 2.3, it's 12.3. All right. Sorry. I can't clear my throat. Any questions on anything we've done up till now? All right, so I think we're on example 3. Is that where you have us?
Well, I left you in early.
Oh, that's right. Okay. Well, I believe that's correct. So, because I'm pretty sure, I don't remember it being a comets orbit, but anyway, that shows that here. Example 3 then is not on the slide set. I can't quit clearing my throat, sorry. So we're going to have to do it on example 1. Let me just make sure I'm saying that right. Yeah, projectile motion is a couple pages off. So, let me get my pen set up for dark. Dark. Okay. And it's not, there it comes. Okay. Example 3, velocity acceleration vectors in space. Now we're in 3 dimensions, and it says see larson-precalculus.com for an interactive version of this type of example. And oh boy, starts off bad. Sketch the path of an object moving along a space curve C given by r of t is equal to ti plus t cubed j plus 3t k. Okay. And that's t greater than or equal to 0. T could be defined everywhere, but they're just choosing to choose only positive t's, which I think I may be thanking them if I think too much about it here. Okay. It says sketch the path of an object moving along that curve, and that's all it says. So I'm going to do my best to sketch, and it's pretty pathetic. Okay, we'll call this the x-axis, this the y-axis, this the z-axis. Okay, let's start with t equals 0. You're right there at the origin, okay, because 0i plus 0j plus 3 times 0, which is still 0k. All right, now t equal 1. Let's do the x, y, Z, 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 okay. T equal 1, you'd be 1 on the sorry, x-axis, 1 out the j-axis, and 3 on the k-axis. So 1, 1 would be right about here, and go up 3 from here. Okay, that would be about 1, 2, 3, somewhere right around there. So it's going from there to there. T equal 2 would be 2i plus 8j plus 6k. So 2i, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5. Oh, one more. 1, 2, 3, 4, 5. And then 6k. Okay. Boy, this sure doesn't look like a very smooth curve to me. Maybe it came up this way, I'm guessing, and now is going out 2 on I, 8 on J, and 6 on K. Somewhere here, so like this. And then the next value would be way further out. And this is, look in the book and see if that makes any more sense to you. Of course, they do their orientation very, very differently from I did. X, Y are over here and Z's up there. Maybe it makes it easier to see, but it's still not a very handy thing at all. Okay? But anyway, whatever the path is, and this is a pretty lousy rendition of it, it says find the velocity and acceleration vectors when t is equal to 1. That's fairly easy. V of t is r prime of t, which would be what? I. That's yes in the Navy. Okay. Plus
3t.
3t what?
To the second.
Squared. J.
J. Plus tk.
3k. Right? Is that what you said? All right. Very good. Now that's the velocity vector. Let's go on and do the acceleration vector, which is the first derivative of the velocity vector, which is the second derivative of the displacement vector. And what would that be?
Again.
Nope.
Wouldn't.
No. That's a constant in front of the I. 1. What's the derivative of 1?
0.
Uh-huh. So 0i, so I won't even write it down.
6t.
6tj.
Plus k.
No, again. Derivative of a constant is 0.
Yeah, right.
Okay, it's just 6tj. All right, so now we're going to do velocity when t is equal to 1. Goodness gracious, I'll write a t again. There's something wrong with the old brain. Okay, v of 1, that would be I
plus 3J.
3j plus 3k, right? All right, now let's see if we can draw that in there. That's the velocity vector. It would be positive in the x direction, positive 3 in the y direction, and up 3 in the z direction. So it would be something, sure hard to write this, something about like that. That's a poor rendition of it, but that would be v of 1. Goodness, I can't write today. I don't know what the problem is. I can't talk either. V of 1. Okay? Now, the acceleration is even easier. A at time t equal 1 would just be 6j. So it's all of acceleration is moving in the j direction, and pretty significantly in the j direction. That's supposed to be a straight line, by the way. But it's that what you see in the book is you can see it's sort of somewhat similar to ours. I chose a poor orientation, but man, I can't draw any of these orientations well. What I can't figure out from the figure there in the book, do you see it?
Yes, sir.
What that y is equal to x cubed line is. I guess that's the line in the, okay, I think I see what it is. That's the line in the y-axis, in the xy plane that's formed, but that's making this a surface, and no surface is given here. But I guess that gives you a perspective of where things are heading. But we are at 113. I didn't specify that, but we had said that earlier, that point that we did, 1 on x, 1 on y, and 3 on z. That is the point that you do your v of 1 and a of 1 from. So anyway, there you have it.
Why is it not 133?
What's that?
Why is it not 133 for the velocity?
What about 133?
I was just asking why is it not 133? Because
What is?
you have your 3t squared j.
Okay. Are you talking about R or V?
V.
V is 133. Okay? And that's what I tried to draw here. The 1 is coming in this direction, 3 in that direction, and 3 up. So it's coming a little bit this way, but more that way and that way. And it's just hard to get any perspective on it. But yeah, that's exactly what V is. V at 1 is...
So I was looking at the book here, it says 113.
Oh, they do. No, that's the point. That's what I was saying. This point, this position here, that's not the vector. That's the position. Or it's the R vector. Yeah. It's 1 on x, 1 on y, and 3 on z. Okay? It's the point is 1, 1, 3. That's your starting point. And then the v vector, starting from there, is 1, 3, 3. And the acceleration vector, starting from there, is just 0, 6, 0. Okay, that's the acceleration vector. Starting from the point 1, 1, 3. Yeah, okay, I see what you're saying.
That's what was throwing me off there, because I was looking in the book and looking at what we come up with.
Well, what should So the book is always consistent. They've given away is 113 is parentheses. That means it's a point. The vector should have had angle brackets. Not saying they always do that, but they should be doing it. All right. So that's example 3. We had already done example 2. Let's move on to example 4. Sorry, I can't talk without gurgling, it feels like. Okay. Here's example 4. An object starts from rest, okay, catch that, from rest at a point 1, 2, 0, okay, and moves with an acceleration of a of t is equal to j plus 2k. So, an object starts from rest. What that means is your initial velocity is equal to 0. That starts from rest, not moving, so it has 0 initial velocity. So that initial velocity is a 0 vector, okay? At the point, and this is a point, not a vector, 1, 2, 0, okay? And moves with an acceleration, a of t is equal to j plus 2k. Now, in this point here, if you wrote it as a vector, that would mean your r, and when I say v, let me go on and specify that a little bit better. Okay, I said v initial, which is true, but it's the velocity vector at time t equal 0. I started to write a 0 and wound up almost writing a 1. I don't know why. And this would imply that your position vector at time t equals 0 is the vector 1, 2, 0. Starting at that point, meaning that is your initial position vector. So basically what we have are 2 initial conditions, initial position and initial velocity, okay? And it tells you the acceleration at all time t, okay? Now, where the absolute value, of the acceleration vector is measured in feet per second per second. So we're in those units. This is feet per second squared. That's in physics, we usually shorten it that way. Find the location of the object after t equal 2 seconds. Okay? Now, what we have to do is recognize that the acceleration vector is v prime of t, right? Which means that is also dv dt. Okay? Now, that's equal to j plus 2k. Well, let's write that in differential form and move our dt over here. And then we're going to integrate. Okay? And that will leave us v as a function of t is equal to, you do the integration.
J squared over 2?
No, okay, now j is a unit vector.
Yeah.
Its coefficient is what you integrate.
So it'll just be 1 squared over 2.
Okay, no. Okay, the variable is t. So the number is 1. Raise it 1 power is 1 to the times t to the 0th power. Raise that by 1, that would be t. Divide by 1, that would be, so this would be, but let's back off a little to it. You could have a constant, I'm going to call it C1 I, because if this is the antiderivative of 0, I, then that meant the velocity vector could have had a component in the I direction. Okay? We don't know that it is, but let's see. C1I plus, as you said, TJ, well, let me back off a minute here too. Let's call it T plus C2J. Is that all right? T plus C2J plus two T plus C3K. Okay? By that sort of? Okay. Now, we know when T is equal to 0, your velocity vector is 0. So let's plug a T in for 0. Okay? Well, that means C1 has to be 0. When T is 0, then C2 would have to be 0. And C3, if V is 0, plug a 0 in for T, you get 0 plus C3, but it's 0. Okay, so all three of those are 0. So none of them panned out. So our velocity vector is just simply T J plus 2T K. That is your velocity vector at any time T. Okay? Because at time T equals 0, that is indeed 0. Okay? But this vector is also your first derivative of your displacement vector, right? Which would be dv dt, and let's do the same, dr dt. Right there. This is r prime of t. That's what the velocity vector is. The first derivative of the displacement vector. And if you rewrite the first derivative as dr dt, then we could do the dt over here, just like we did before, and integrate. And this will give us, in integrating the dr, would just be r. I'm about to throw my pen away. So r of t would be equal to, what's the antiderivative of t?
I'm still trying to get that line above it.
Oh, this right here.
Yes, sir.
The whole line?
Pretty much.
Okay. This is r prime of t, which is also dr dt. That's also v of t. And that was C1I, but C1 was 0 because the initial velocity is 0. The 0 vector. All three components are 0. So that means C1 is 0, C2 is 0, and C3 is 0. Because when you plug 0 in for t, this gives you 0. Then you would have C2I, but that has to be 0, so C2 has to be 0. When you plug t equals 0 in here, that gives you 0 plus C3K, but K is also 0, so C3 has to be 0 as well. Okay, so then we're going to take that, and since this is dr dt, multiply our dt over there, keep the dr, so this gives you r of t is equal to, now again, when you integrate your I, it's 0I. When you integrate 0, you get a constant. So, you mind if I call it C1 again? Because those are all 0. New C1's here. Or we could call it something else. D1, okay, let's call it D1. D1 I plus, okay, antiderivative of T. T squared over 2J, plus D2 J. All right, here's, doing example 4 on page 839. I think, isn't it? No. Yeah, that's it. Yeah. Yeah. Huh? Oh, I'm sorry. Goodness gracious. Brian. Okay, sorry about that. Sorry about that. All right. Okay. Now, without going back over it too much, the wording says an object starts from rest. As soon as you hear that, you know the initial velocity is 0. Initial meaning when t is equal to 0, your velocity vector is the 0 vector. 0I plus 0j plus 0k. Anytime you see initial, starts from rest, that means it's not moving, so velocity is 0, every dimension. Okay. And it starts from rest at a point, so this is your r of 0 is equal to I plus 2j plus, 0I plus j plus 2k. Okay? So that means here we go. Your r is I plus 2j plus 0k. So that is your initial position when t is equal to 0. That's the point you're starting from, which means that's the terminal point of your displacement vector, right there. Okay. Now, your acceleration vector, they told you, was j plus 2k, period. Okay? Now, first thing we did was write this as dv dt. Okay, v prime is a, and that is dv dt. And move the dt on that side, integrate dv, you get v. Okay? Integrate 0I, and you get c1i. Integrate 1j, you get t plus c2j. Integrate 2k, that would be 2t plus c3k. You have to have a constant in there for indefinite intervals for each component. Okay? So that is your velocity vector. But your initial velocity vector when t is equal to 0 is a 0 vector. All these are 0. So that means c1 has to be 0. When t is equal to 0, this is 0 plus c2. Well, that has to be 0, so c2 is 0. When t is 0, this is 0 plus c3, but c3 is 0. So they're all 3 0. So you don't get anything but tj plus 2tk. I didn't put my hat on the k. And why did you let me get away with that? Okay. Now, that is your velocity vector. So that's also the first derivative of your displacement vector. In other words, dr dt. Integrate both sides just like we did before, and this gives you r of t. Now remember, you have a constant. You have a 0I here, because this is three-dimensional. 0I, so this would be, we said a d1i, because derivative of the constant 0, so that gave you 0I, plus t squared over 2 plus d2j. Have to have a constant for that one. And this would be what? Antiderivative of 2t would be? T squared plus d3k. You have to have your constant in there. Indefinite interval. All right? But we also know what your initial displacement is. When t is equal to 0, then this initial displacement is 1, 2, 0. So in other words, your d1 here is 1. Okay? So this will just be I plus, okay, your second component is 2. Okay? Well, that says that when t is equal to 0, of course this is 0. 0 over 2 is 0. And this would be 2j. Okay? So that means your r of t would be t squared over 2 plus 2j plus And when t is equal to 0, this will be 0, and you're supposed to have a 0k. So v3 is equal to 0. So you just have t squared k. All right. There is your displacement vector at any time t. Okay? Now, that's your displacement vector at any time t. R of t is equal to that. Why were we doing all that? Because this question said, find the location of the object after t equal 2 seconds. So what you do now is just plug in R of 2. And what would that give you? That's just an I, one I. So that'd be I plus, huh? 4j. Okay. T, 2 squared is 4 over 2 is 2 plus 2 is 4j plus 4k. So where are you? You're at the point 144. Okay. And that's what they show in the text as well. So they just write it like this, but in the picture they show you winding up at 144 at t equal 2. Make sense? All right. Now we're ready for projectile motion. All right. You now have the machinery to derive the parametric equations for the path of a projectile. We kind of just did, okay? Assume that gravity is the only force, only we weren't dealing with gravity then, we were just dealing with the formula we had. Assume that gravity is the only force acting on the projectile after it is launched. Obviously, to launch it, you had to do a force on it. Fired a gun, threw something, you had to do it. But as soon as it's launched and it's left the barrel of the gun, left your hand if you're throwing it, whatever, then the only force acting on it is gravity downward. In real life, there's always a little bit of air resistance. We're going to ignore air resistance, okay? So we're going to assume gravity is the only force acting, okay? After it is launched. So the motion occurs in a vertical plane, okay? Vertical plane here. We don't have 3 dimensions in it yet. Maybe we won't have, but not yet. So the motion occurs in a vertical plane, which can be represented by the xy coordinate plane, okay, coordinate system, with the origin as the point on the Earth's surface, shown here, and you're assuming some initial height. Now maybe that was 0, then you bring the A on down to the bottom. But we don't know that, okay? You're given an initial velocity here, which is whatever that is. Now the last example said you had an initial velocity of 0. Well, if that were the case, it probably isn't going very far, but you gave an acceleration, but it wasn't the acceleration due to gravity. So that wasn't exactly projectile motion because of that. But you're given some initial velocity, some x component and some y component, looks like more y than x. Okay? But the only force acting on it is gravity. The only acceleration acting on it is gravity, which is, and they didn't give units here, whatever the acceleration of gravity of those units is. Okay? So, this is at t equals 0. They tell you you're at t equal 1 there. Okay? No. T1 there. This is at t0, t1, and this is at t2. So you're moving pretty quickly here, I guess, depending on how big the t's are. And that's your motion. The velocity vector is always tangent to the curve. Always. The acceleration vector is always straight down. Okay? So those are your 2 always there. All right. So what can we do with that? For a projectile of mass m, and they don't give you units for that, But here you can almost guess you're dealing with SI system because we don't deal with mass too much in the U.S. customary system. So your force downward is mg minus mgj, okay? So it's always pointing downward, only in the y direction, since that's your vertical direction, pointing downward, meaning acceleration is downward. The force is mass times the acceleration due to gravity. Where the acceleration due to gravity is 32 feet per second, or feet per second squared, or 9.8 meters per second, or meters per second squared. By Newton's second law of motion, the same force produces an acceleration of A of t, which is just g. Okay, satisfy the see why they don't just call it b, but they are. Satisfies the equation F equal ma. Consequently, the acceleration of the projectile is given by ma is equal to minus mgj, which implies that a is equal to minus gj. Okay. A is an acceleration, so it's a vector. G is the magnitude of the acceleration, which is this, or that, whichever happens to be. So that's a scalar, but it always is pointed that way. Okay? So here's example 5. All right. Projectile of mass m is launched somehow from an initial position r sub 0 with an initial velocity v sub 0. Okay? Find its position vector as a function of time. Okay? That's all they give us. Okay? So find its position vector as a function of time. Well, where you start is with that acceleration. So the acceleration vector is minus g times t. No, minus g. J, I'm sorry. There's no time dependence on it. It's just a constant g, but it's in the j direction if you're using xy plane. Okay? Now, that's it. That's where you start. Okay? The only force acting on it is acceleration due to gravity, which is always pointing downhill, negative direction. And that acceleration is g. That's the value of it, whether it's 32 feet per second squared or 9.8 meters per second squared, or whatever the acceleration is, that's what you got. Okay? And we do it just as we did before. This is also dv dt. If you multiply both sides by dt, and so this will give you, when you integrate this and integrate this, this gives you the velocity as a function of time is equal to, goodness gracious, I'm stiff, minus g, acceleration due to gravity, and whatever units those are, times t, well, remember we did this before too. Minus, that's not quite the best way to do it. I'm going to put the g back on the inside with the j. Okay, that way. Okay. Notice your I component is 0 of your acceleration, but that means your initial velocity could have a component. So we'll call that v sub 0 x, okay, for the whatever the velocity is initially in the x direction, okay, minus, and when you integrate that, excuse me, when you integrate that, you get, boy, I can hardly talk, minus G, I'm going to put a, wait. Let me clean this up just a little bit. Okay. What I said was right, but I just didn't write it well. V sub 0x in the I direction, okay, minus when you integrate that, you get GT plus V sub 0 y in the j direction plus in the k direction, it was a 0 component, so it's some constant. So I'll call that V sub 0 z k. All right. All right. Now, what is your V sub 0 x? I is V sub 0 y. That is your velocity vector, V sub 0. Okay? So the easier way to write this would be this. Minus gt in the j direction plus v sub 0 of t just v sub 0 t, because that's your x component, y component, z component. So that's really the simplest way to write it. Okay? Now, this, though, remember, is your dr dt. Okay? Pretty rugged there. So when you integrate that and this with respect to time again, okay, you really need to do it up here. And I'll show you why in a minute. Okay, so when you integrate that, you just get your r of t, which is equal to, now when you integrate this, this will be v sub 0 xt in the I direction. Whoa. V sub 0 xt, that's what you get from integrating that. But then you also get a plus r sub 0 x okay. My r's and v's are looking too much like each other. R sub 0 x, and this will be in the I direction, plus, now integrate this one, and you, actually this one up here, and you get a well, I'm going to put a plus, and I'm going to put a minus gt squared over 2 plus v sub 0 y.
R or v?
I'm sorry?
V sub 0 xt plus.
Okay, this is the r. And that's supposed to be an R. I can't read my own writing here. No. That's V sub 0. Right. No, that's the, yeah, that is correct. This is R sub 0. That's V sub 0. This is also V sub 0 y times t plus R sub 0 y. Okay? Well, wait. The components aren't vectors, so you don't need the arrow over them. Okay? And this is all in the j direction. Okay? In other words, you're integrating that, t squared over 2, integrating that, t, and then there's your constant integration for that. That's your r sub 0 y. Okay? Now, the final one there, when you integrate that one, boy, that's hard for me to read. That would be plus v sub 0 z and the times t plus r sub 0 z plus r sub 0 z, and that would be times k. All right, there's your vector. Now, writing it in a little bit neater form, you've got your minus g t squared over 2 in the j direction, now plus, notice what we have here, v sub 0 x in the I direction times t, v sub 0 y times t in the j direction, v sub 0 z times t in the k direction. So that's just your velocity vector, v sub 0, that is a vector now, as a function of time in the, wait, it is a function of time, but it's times t, and that's what I really meant to do. So let me not put the parentheses there. Okay, just write it like that, v sub 0. Let me write the t in front, okay, that makes it simpler. Plus t times v sub 0, that's a vector v sub 0, and then plus r sub 0, and that's a vector, r sub 0 I plus r sub 0, r sub 0 x I plus r sub 0 y j plus r sub 0 z k. So that's it. There is then your displacement vector. These each have x, y, and z components. This only has a y component. And this is your how it's being displaced downward. But then you have your initial velocity and initial position all contributing to its final position. Okay. Now let's see if that's anywhere close to what the book wrote it as. Yeah, minus 1/2, they wrote 1/2 in front, g t squared j plus t v0 plus r0. Yeah. That's your position vector. Okay. Now, there is some verbiage here that's fine. And there seems to be two different, well, no. They're talking about how you can express this in a couple of ways. We've had t as the independent variable throughout this. But now they're saying that if you choose your theta to be your independent variable, that in any kind of motion, your x-coordinate is r cosine theta, and your y-coordinate is r sine theta. So they just give you another way to express what we just said, but in terms of theta, rather, though t's are still in there, it's, yeah, they're sort of mixing them up pretty badly. But let's move now to, oh, sorry, forgot. This one you can see the answer. This is the same problem. So let's see how they begin with the acceleration vector. A of t, that's a vector, is equal to minus g, that's acceleration due to gravity, minus meaning it's downward, g is the magnitude of it, j is the direction of it. Okay, integrate it twice. First time you integrate that, you get, because a of t is equal to v prime of t, or dv dt, do the v over here, the dt over there, and go to town, and this acceleration has just got a component in the minus j direction, minus gj dt, okay? But you also have the c1, which is your x component of your velocity vector, okay? And why they chose c1, I'm not sure. I like v sub x because that tells me that's the x component of the velocity vector. I'm going to forget what that is in a little bit, okay? And then you integrate that again because v is the rdt. So you integrate that and get r. And when you integrate that with the dt over there, this gives you minus 1/2 gt squared. Oh, I'm sorry. This C1 is your initial velocity vector. It's the whole vector, not just the y component. That's the whole initial velocity vector. Okay? So then you get C1t plus C2, where C2 is your initial displacement vector. Okay? Position vector. And then at the end, you can use the initial conditions that v of 0 is equal to r is equal to v sub 0, r of 0 is equal to r sub 0, and you solve for the constants vectors c1 and c2, and basically you get c1i is equal to v0, c1 is equal to v0, c2 is equal to r0. Therefore, the new position vector, when you plug those in, will be the minus 1/2 gt squared, that's the component due to gravity, and then tv0, which has x, y, and z component, depending on what that was, plus r0, which has x, y, and z components. So that's as generically as you can write the position vector, same way we did. Okay. In many projectile problems, the constants r0 and v0 are not given explicitly. All right, here's what they're doing with the theta z. Okay, sorry. Stop that. What they do give you is your initial speed, which is the magnitude of your velocity vector initially, or your initial height, which is the magnitude of your position vector, at time t equals 0. You're often given initial height and initial speed, and the angle at which the projectile is launched. Well, your initial height is merely going to be your initial position vector, and generally, if that's just a height, that's in the positive j direction, y, x, okay? So that would be hj, you might say. Now, initial speed is like this, and that's usually just the magnitude. And that's where it comes into play. That's your magnitude of this times the cosine of that will give you the magnitude in the x direction, and the magnitude of this, v0, times the sine of this angle theta, that will give you your y value in the j direction. So x is magnitude of the velocity vector, and usually that's what they give it to, initial speed. So that would be initial speed times the cosine of the angle theta. If you know the angle that it launched it at, and the y value, y component would be the initial speed times the sine of that angle theta, if they gave you that. All right, from the given input then, you can deduce that r sub 0 is equal to hj, that's what I was saying before. And because the speed gives the magnitude of the initial velocity, it follows that your initial speed, which is what they gave you, is that magnitude. So you can write this as goodness gracious, rather bizarre. Your initial velocity is v sub 0 times cosine theta I plus v sub 0 times sine theta j. I don't know why they just didn't call that initial speed. That's what the problem gave you, but they kept putting it in as the magnitude of the initial velocity, and that is indeed what it is. I component is in this way. Sine theta is the opposite side. Okay. That's if they give you the angle theta. Now, so the position vector can be written as the form. This is exactly what we had before. The position vector is minus 1/2 gt squared j plus t v0 plus r0. That's exactly what we had before. But now we can rewrite that as this is your exactly the same j here. The t and this velocity initial velocity vector is your v0 cosine theta I plus t times t0 v0 sine theta j, and then your initial position vector is just hj. Okay? So if you split these out independently, t v0, only now they're right, v0 cosine theta first, that's a constant, times ti. Now, your j component has the h from there, the v0 cosine theta, sine theta from there, and the minus 1/2 gt squared there, and all that is your j component. Now this is just two-dimensional motion, planar motion, vertical, horizontal. This is your horizontal motion, there's your vertical motion. Now something to note here, this is a constant. The speed is a constant speed in the x direction. At that constant speed, the more time you travel, then it's just velocity times time. That's how far you go in the x direction. Your y component, you start at the h, initial velocity upward, but then gravity is pulling you downward. So you always have the initial, and this is usually fired up, so that would be positive to begin with, and then your acceleration due to gravity is downward, so it's slowing you down. So you have parabolic motion in the j direction, constant increasing velocity in the j direction, in the I direction, sorry. So here's theorem 12.3, position vector for a projectile. Neglecting the air resistance, the path of the projectile walks from an initial height h, initial speed v0, and angle of elevation theta is described by your r of t would be your v0 cosine theta t I. That's your initial, your horizontal component of your velocity. Never changes, but the longer it goes, the further it goes, so that multiplied by t. That's your I, and only one I component. Your j component is your initial velocity plus your component of your initial position, the vertical component of your initial velocity times t, and then minus 1/2 gt squared is your acceleration downward, always. Where g is acceleration due to gravity. Depends on what unit you're measuring in. US customary or SI. All right, so here is example 6. Finally got to an example here. A baseball is hit 3 feet above the ground. Seems like I've seen Clark with a baseball shirt on before, right? That's a pretty sweet spot, right about 3 feet above the ground, okay? Waist high, approximately, okay? Baseball hit 3 feet above the ground at 100 feet per second. That means that's its initial velocity, feet per second, velocity measure. At an angle of 45 degrees, I'm going to tell you right now, gives you maximum range on that. Any higher, it's going to come short. Any slower, it's going to come short. Maximum range of 45 degrees with respect to the ground. as shown in this figure here. Find the maximum height reached by the baseball. That would be the maximum Y value. And then the question is, will it clear a 10-foot high fence located 300 feet from home plate? We'll see. Okay? So let's see what we've got here. This is your H from the last example, initial position. That's in the J direction. Okay? So your R0 or time t equals 0 is equal to 3J feet. Okay? 3 feet J, or however you want to say that. Okay? This is your V sub 0, initial speed, 100 feet per second. Angle 45 degrees, huh? Oh.
So that 1/2 GT squared, or minus 1/2 GT squared is just sort of a standard.
Yeah, acceleration due to gravity, okay? That's it, exactly. Angle of 45 degrees, so that's going to be your theta, okay, that we were talking about, with respect to the ground, as shown in this figure. Find the maximum height reached by the baseball. Okay. So, guess the best thing to do would be to write your formula down, if you remember what it is. Your R of t is equal to, remember your x component was your V0, initial speed, that's your 100 feet per second, times the horizontal component is cosine 45. And because it's 45 degrees, that's going to be the same thing, either sine or cosine is going to be the same, times t, and that will be in the I direction. And then the second part is going to be your initial displacement, your h, which is 3 feet. I'm just going to keep it in values here. H, and there's Vince. I marked you present earlier because I was psychic. Okay, so there is your area. Okay, we're doing example 6 on 841. Now, I guess y'all are doing a tag team, so he comes in and you leave the ring. Oh, okay. All right. Yeah. Okay, so initial position was H, and then you went up or down, V sub 0 sine, I put in the 45, not being very consistent, T, and then your drag downward due to gravity is minus 1/2 GT squared. And all that is in the J direction. Okay. Now, says finds the maximum height. Okay. All right. One way you can do this is your range, okay? This is your height at any time, because that's your J. So what you could do is take the first derivative with respect to time of that to find out when you reach the maximum height, okay? So let's do that. Let's take the derivative of just this component here. So I'm going to say d r sub y dt, that being that component. Well, this doesn't contribute anything. That's a constant. And this would be the V0 sine of 45. That's a constant. Let's just write what that is. That's 100 times the sine of 45. Well, sine of 45 is root 2 over 2. So basically 2 goes into 100, 50. So it's 50 root 2. Okay? So 50 root 2 minus, and then derivative of that would be GT, right? But we know what G is too, since we're in the U.S. customary system, feet and seconds. We know that's going to be 32 feet per second squared times t. Okay? So in other words, and you want where this is equal to 0, so that says where 32t is equal to 50 root 2. Or t is equal to 50 divided by 32 would be 25 divided by 16 root 2. Plug that in and see what time that gives you. 25 root 2 divided by 16. Anybody?
2.209.
Okay, about what? 2.09. Okay, approximately, something like that. All right, that's going to be when it reaches its maximum height. Let's plug it in and see what the height is then. So that would be your 3 plus 50 root 2 times that number, 2.209, okay, minus, running out of room here, 16, because 1/2 of 32 is 16, times 2.209 squared. Okay? Plug that in and see what you get. What?
You don't have to plug it into the old part position.
What's that?
You won't have to plug it into the old part position.
You mean right here? Okay, not yet. Okay? All you want is what the maximum height is. So you want what the J component is at this time t. This is in seconds, by the way.
81.125.
81.125 feet. Okay, let's see if they got anything close to it. They got 2.21 seconds, which is pretty close to what we got. They rounded. So they rounded about 81 feet, which is a good rounding. And here's Daniel here. We may actually get a majority. We do now have a majority of the class here. Not for very long, but here. Okay. Now, that's the maximum height. The question, though, will it clear a 10-foot high fence located 30 feet from home plate? That's your question. So, what you want to know is that your R of t, is there any time t when R will be 300, the x component of R will be 300, so this will equal 300, and this part here equals 10. Will that ever happen? Okay? So, let's see first how high, well, yeah, this will do it. What time the ball will reach 300 feet, right? So we just divide. Here's what we've got, is the x component at 300, so that, and the v is 100, so we have 300 equal 100 times root 2 over 2. That's what cosine of theta is, t. Okay? So let's divide both sides by 100, and that gives you a 3 here. And this is, root 2 over 2 is the same as 1 over root 2, so 3 root 2. That's going to be the time at which it reaches that. So someone tell me how long that is. 3 root 2. What time is that? 3 times root 2. 3 times 1.414.
4.243.
4.242 seconds. Okay? Now that's when it reaches 300 feet. Let's see how high it's going to be when it reaches 300 feet. So plug that time, you have it on your calculator, plug it in here, and for T, and let's see, yuck, don't have much room left to write. Let me erase some of this stuff at the top. We know what those are now, I think. Okay, so we're going to plug in that time into this. So we have 3 plus 100 times root 2 over 2, that's the sine of 45, times 4.242 minus 1/2 32 times 4.242 squared. See if that's greater than, less than, or equal to 10 feet. Will it make it over the top of the wall? See what the height is then. Now you can make life a little easier by going and dividing by 2. That would be 50 root 2 like we did before. And then half of 32 is 16. I think we did that before too. If you already had done the other, that's fine.
15.0.
Oh yeah, it's going to clear the fence. Okay. In fact, clear it well enough that even the best left fielder out there pushing off the wall and everything else is not going to get up to 15 feet. Yep, he got it cleared. Okay. And let's see what they got. 81 feet. 15 feet, yes. Okay. It does clear the 10-foot fence. For a home run. Unless, of course, that was in foul territory. I don't know. Okay. For me, if it ever hit one that far, it probably would be foul. Okay. I don't think I'd ever hit one that far. Homework exercises 12.3. Do any of the odds 3 through 9? They're all at Calc Chat. 3's at Calc View. Do any of the odds 11 through 19? They're all at Calc Chat. 15's at Calc View. Do any of the odds 21 to 25? They're all at Calc Chat. 21's at Calc View. Do any of the odds 27 to 39? They're all at Calc Chat. Wow. Okay. Then 41 should be at Calc Chat. 43. Do any of the odds 43? No, do 43. It should be at Calc Chat. Do 45. It should be at Calc Chat. Either 47 or 59 or 49. They're both at Calc Chat. And either 47. I'm sorry. Any of the odds 47 to 49. They should be at Calc Chat. I'm sorry. They've got something wrong. Oh, no. I'm sorry. Sorry. 47 through 49 or 49, they give you something. Then it says use the results of those to do 51. Sorry. And then you can think about doing or explore doing 53 or 55, and then you can do 57 if you'd like. 59 is a proof. You can do that if you like, and there's a true-false 61 or 63. All right, good deal. We'll continue with and go into 12.4. Okay, we've still got about 20 minutes, right? Okay. So, let's see how they did the problem. You're given h is equal to 3, v0 is equal to 100, theta is equal to 45. So using that, with g equal 32 feet per second, or feet per second squared, that will result in 100 times cosine of 40 the pi force, which of course is. Why they went from 45 to pi force, I'm not sure, but it's root 2 over 2, okay, whatever it is. Okay, t plus 3 times 100 times sine of 45 degrees, or pi force, it doesn't matter which, t minus, and then they did 1/2 of g, which is 16 t squared j. Okay? There's your basic formula, which is 50 root 2 t plus 3 plus 50 root 2 t minus 16 t squared j. First is the I component, second is the j component. Velocity vector would then be why in the world are they doing that? It's fine. I don't know why they're doing that. Oh, I know why. Okay, got it. Remember, they said when it reaches its maximum height, the vertical component will be 0. That's why they're doing it. We got there another way, but they did get there. So that's where 32t is equal to 50 root 2. I remember doing that. And that, sure enough, is what they got. So it's 25 over 16 root 2, which all came out to 2.209. They did 2.21. Okay? So that's when it reaches its maximum height, plugging back into the y component, and you get 649 over 8, which is about 81 feet, okay, when t is equal to 2.21 seconds, 2.209 seconds, okay. Then the ball 300 feet from where it was hit, that's going to be your x component, so you set that equal to your 50 root 2 t. Now, let me say this. It's been bugging me the whole time, and I just resist saying it. I really don't like writing root 2 t because, especially when I write it, I can't always tell whether the t is under the radical or not under the radical. It's even a little hard telling here. So what I would do is 50t root 2, or put it in parentheses or something other than writing like that, okay? But then that's equal to 300. Divide by 50 root 2, and you get 3 root 2, which is exactly what we got at 4.24 seconds. We got 4.242 seconds, I believe it was. But and then at that time, the height of the ball was this, 3 plus 50 root 2 times 3 root 2 minus 16 times 3 root 2 squared. And it happens to be all the root 2's go away and you just have regular numbers there. 303 minus 288, and that's 15 feet. Yes, you made the 10-foot fence with room to spare. All right, and that was the end of the section. So let's go now to 12.4. That part, much of this last part, has been two-dimensional motion. Though we did do some three-dimensional earlier on, the last part was all two-dimensional. Okay? Now we're moving to, again, chapter 12, vector valued functions. Now we're doing tangent vectors and normal vectors. Okay. Now, we talked about tangent vectors before, same as velocity vectors, but we didn't talk about normal vectors. Now, most of the time, not all the time, this is dealing with three-dimensional, though you certainly can still do it in two-dimension as well. So what we're going to do, objectives to find a unit tangent vector and a principal unit normal vector. Now, when you see the word principal, you kind of should bring to mind, you could have a plus or a minus here. We're going to take the plus, or we're going to take just one of those. And that's what we mean by the principal unit normal vector at a point on a space curve. So again, they're implying this is three-dimensional, but it could be two-dimensional, but we are going to deal mostly in three dimensions. And we'll find the tangential and normal components of your acceleration. Again, basically in three dimensions. Okay? All right. The velocity vector points in the direction of motion. Always. Okay? And that is always a tangential vector. This observation leads to the next definition, which applies to any smooth curves, not just those for which the parameter represents time. any smooth curve. And we may still be using t, but it won't necessarily be time anymore. So here's the definition of a unit tangent vector. Let C be a smooth curve represented by this vector r on an open interval I. So your t, whatever that stands for, is good over some interval. The unit tangent vector, and that we call a capital T. It is a vector, so it's bolded here. When I write it, I have to put an arrow over it. Capital T of t. This little t has nothing to do with time, nothing to do with tangent. That's just your parametric variable. Could be anything. This t is a unit tangent vector, so that's why they put a capital T. Oh, and if it's a unit tangent vector, when I write it, I'm going to put a housetop over it to remind you it is a unit vector. Okay? At any time t is defined as unit tangent vector. First, your first derivative of your displacement, whether you're talking, okay, I'm sorry, I said displacement, of your r vector. Well, that basically is a displacement vector, or your whatever that r stands for. Okay? May not be a displacement, whatever it stands for. The first derivative of it is going to be like your velocity. It doesn't need to be a velocity. Like your velocity, it's in the direction of increasing t. Okay? And it's going to be tangent to it. However, it's not going to be a unit vector. To make it a unit vector, divide by its magnitude. Okay? So this is where we get the unit tangent vector in the direction tangent to the curve. And this can be a three-dimensional curve. Technically, it can be an n-dimensional curve. We're going to stick with 3 or 2. Now, this, of course, is assuming that your first derivative is not the zero vector. If it was, it doesn't have a unit tangent vector. There's no direction to it. All right, we know that a curve is smooth on an interval when r prime is continuous and non-zero on the interval. So therefore, the r prime can't be 0. So smoothness is sufficient to guarantee the curve has a unit tangent vector, because smoothness means there's no, it's continuous and non-zero everywhere on the interval. Okay? So that's your unit tangent vector. Pretty simple expression. So let's do one. Find the unit tangent vector of the curve given by r of t is equal to ti plus t squared j. And we're going to do it where t is equal to 1. So what you reckon the first thing we're going to do? Going back to this. What looks like a good thing to do? Take a derivative. That's usually good in a calculus class. So we'll do r prime of t. And what would it be? Second?
I plus 2t.
A little up.
I plus
Oh, yeah, exactly. I plus 2tj. Perfect. Okay? Now, what's the next thing we want to do with that? Find its magnitude. So the magnitude of this, of r prime, is going to be the square root of 1 plus 2 squared, t squared, so that would be 4t squared. Right? Perfect. Okay? We're almost there. What would then be the unit tangent vector as a function of time? Yep, it'd be I plus 2tj over the square root of 1 plus 4t squared. That's it. Okay? Now, if you want to write it that look more like a vector, you could do 1 over the square root of 1 plus 4t squared I plus 2t over the square root of 1 plus 4t squared j. If that makes you happier and you think it's more like a vector, writing it that way, that's fine too. But what we're interested in is where when t is equal to 1. So what is the unit tangent vector when t is equal to 1? 1 plus 2t squared. 1 plus 2t squared. 1 plus 4t 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 squared. 1 plus Let's do this form, okay? That would be 1 over can you read my writing? The square root of 5i plus huh? 2 over root 5j. Okay? Now that's what we claim. One good way to check is to see if indeed this is a unit vector. How would we do that? The square root of this squared plus that squared. What's this squared? 1 over 5, right? That squared? 4 over 5. 1 over 5 plus 4 over 5 is 1. Square root of 1 is 1. Yes, that is a unit vector. Doesn't guarantee it's a unit tangent. It is a unit vector. It doesn't guarantee it's a unit tangent vector, but I don't see how it can help it because we did it right. Okay? So there indeed is, now they wrote it this way, which is perfectly fine. Now let's go out for a minute. 1 over root 5 times I plus 2j. I don't know why they chose to write it that way, but it's fine. That's perfectly good. Okay. All right. Let's clear my scratch here. Any questions before I clear it? All right. And let's see how they do it. The derivative of r, that's exactly where they started. It's I plus 2tj. Perfect. Unit tangent vector, then r prime over r, the magnitude of r prime, which would be r prime, we wrote, and the magnitude of r prime, they didn't write it down, but is square root of 1 plus 4t squared times that, so they pulled it out anyway, and then you substitute t equal 1, little t equal 1, and you get 1 over root 5 times I plus 2j. Okay? Now, here is that representation of that function we just had. RT is equal to that. This could have been saying that x is equal to y squared. I mean, y is equal to x squared. That's what I meant to say. And that would be the parabola here. There you're at t, when t is 1, you're there at 1, 1, and you're going up in a direction parallel to 1, 2, okay? Okay? So the velocity vector or the unit tangent vector is in that direction. All right. Make sense? All right. That's example 1. Okay. All right. They have a little statement at the bottom of the page here saying in example 1 that the direction of the unit tangent vector depends on the orientation of the curve. For the parabola described by a different function, the t of 1 would still represent unit tangent vector, but would point in the opposite direction. It says try verifying that. You want to or move on? What you think? No one's listening. There's one. Okay. Want to do that quickly before we move on? Here is your r vector. Different r vector here. And this is minus t minus 2 in the I direction plus a t minus 2 squared in the j direction. Okay? It wants you to find your unit tangent vector of this one. So what would you do first? R prime of t, and what would that be? Negative I plus 2j, right? Up 2tj, which is not exactly what we had before, but awfully close. We had a positive I plus 2tj. They have a negative I plus 2tj. So that would be going in the opposite direction. At the same point, well, we got to see if it's at the same point. Let's plug that in and see. When t is equal to 1 here, this would be a minus, this would be a 1 minus, that would be a minus 1. Minus 1 is 1i, and this would be 1 minus 2 is minus 1 squared is 1j. So yeah, you'd be at the same point, but now the velocity vector would be going down this way. Okay? So your r prime vector would be in that direction. But everything else would be the same. Because the magnitude of this is the same. The only thing the difference is as the sign of the unit tangent vector would be negative on the x, same thing on the y. Okay. I don't know if that's as quickly as they wanted me to do it, but I did it. Okay. I've lost where I was. There we were. All right, so let's move on. The tangent line, I don't have much time. The tangent line to a curve at a point is the line that passes through the point and is parallel to the unit tangent vector, right? Tangent line to a curve is at a point, is the line that passes through that point and is parallel to the unit tangent vector. So basically, you have to do manipulations of that like we did a long time back. In example 2, the unit tangent vector, one we just did, I think, no, one we're going to do. Unit tangent vector is used to find the tangent line at a point on a helix. Helix is a sort of a spiral that's going up like that. Are we going to have time to do it? I kind of doubt it. So let's plan to stop there, okay, and pick up there next time. We just barely got enough done to do maybe a couple of examples in this section. Yeah, you can do any of the odds 3 through 7. They're all at Calc Chat, 5's at Calc View. And then we'll hold off and do the finding of the tangent line after we do the next example. All right, good deal. Any questions? All right, let's just do a quick look ahead here. We don't have a lot of time left. Y'all were in here when I made the original announcements. We have class next week for 2 days and Monday of the following week. So hopefully we will get most of the way through chapter 12 by then. Yeah. We may even get a little bit into 13. We're not going to get enough for me to test you much on anything, so I think the chapter 12 test will be your last test. But I do want to introduce you, because we really should have gotten there, the concept of partial derivatives. Okay? I'll probably cut through a lot of the stuff at the beginning and just show you how to do partial derivatives. And then if we can, that is chapter 13, I'm not going to do anything but just introduce you to it. Chapter 14 is kind of the reverse of that, and that's multiple integration. Okay, and again, just give you a quick overview of how to do that. So what we'll try to do is finish chapter 12, which is just the rest of 12.4, which we started today, and 12.5 is it. And we'll try to get that done Monday and part of Wednesday of next week, and then I'll use the last part of Wednesday and the following Monday to just give you enough for you to go on to do partial differentiation and multiple integration. Won't test you on that, test you just on chapter 12. How's that? All right, good deal. That may have eaten the rest of the time we have, so any questions?